Hi, I'm Filip Radenovic, and I will present our work modeling in 3D modeling in the dark from large unordered image collections. As the title suggests, we are pushing the limits of 3D reconstruction in difficult lighting conditions, as difficult as the ones shown on this slide. Well, maybe not as this hard, these are almost black, but let's still see what we can do. So let's consider two types of dense 3D reconstruction. In the first type, we use all images, both day and night, to build a dense 3D reconstruction. We call it standard dense, and this is known to produce artifacts because the illumination in day and night images can be arbitrarily different. The second approach is to split images into day and night and then build a separate model on these two clusters. This produces clean reconstructions. Let's now see what the problems are in both of these two types of reconstructions. So, for example, for standard dense, there are artifacts appearing both in structure and appearance. So, for example, here, or actually everywhere. And these artifacts don't appear in separate day and night dense models. However, not everything is perfect. There are problems also in separate models. For example, some parts in night model are just too dark to be reconstructed. So what we do is we geometrically fuse these two models to produce a complete model, and then we learn at color transfer to recolor the areas that were not reconstructed in one of the models. So to go through the pipeline, we start with a large unordered data set. And using techniques like image retrieval and structure for motion, we build a sparse model. The sparse model contains both images of day and night due to color normalization of local features. And this is facilitated by the transition images like dusk and dawn. Now we want to split the registered images into day and night, and we do that by observing the relation between images in 3D points in scene graph. We actually do a graph cut on the scene graph, and the color histograms of images are contributing the energy that is being minimized. So finally, when we split the images, we build the separate dense models. Although they share the same sparse model, as I said before, they still differ significantly in completeness and appearance. That's why we do the geometric fusion, and we can do it because the underlying structure does not change at day or night. We also learned the color transfer between the parts that were reconstructed in both models so that we can recolor the areas that were not reconstructed in the other model. So at the end of our pipeline, we actually get a complete model either in day or night with a realistic illumination. Our contributions are automatic reconstruction through clustering of day and night images, then geometric fusion of day and night dense models, and at the end, learning a color transfer so that we can recolor the unreconstructed areas in one of the models. At the end, I would give a glimpse of results. If you want to see cool day and night reconstructions, please come to poster number 21. I was there since dawn, and my advisors are making me wait for you until dusk, so please come, and thank you for your attention.